Proof by equivalence. So the last lesson was a proof by deduction. And the deduction we went left to right specifically. If we had A implies B, we start with A, we try to imply B. But what if we want to do A and B, what if we want to show that A and B are equivalent? Then we have to do both ways. We have to go A implies B, and we have to do B implies A. So do like proof by deduction both ways. So is there a short way to do that? Yeah. We can do a proof by equivalence where we work on both sides. Right, so that's what this one says. However, if we can construct an argument so that each deductive step is an equivalent step, then we can prove A implies B and B implies A at the same time. So basically, if we have an equal sign, we can work on both sides and just show that they match. That's a proof by equivalence. And we've been doing this for years. Anytime like you try to solve for zero, like you try to solve like an equation equals another equation, that's a proof by equivalence, right? Where we work on both sides, like they do here. Like, oh, this guy equals that guy. We expand this out. We set equal to 0 because we're subtracting both sides. That's a legal move. And you solve your answer. That's a proof by equivalence. So what are the legal moves? Same thing we've been doing since Algebra 1 equivalent, right? You could add subtract the same term from both sides. You can multiply by both sides as long as it's not by 0. And you can substitute an equal term for another equal term. So this is proof by equivalence. Again, we've been doing this forever. There's some other operations which maintain equivalence. For example, rules of logs. You take a log of both sides. You gotta watch out though when you square or take the square root of both sides, right? All the stuff we know from when we solve equations. Right, if you square root both sides, you might get a plus or minus, it might not be, or you square both sides, you get rid of a plus or minus, it's not gonna maintain equivalence. This is why when we try to solve something like this, given that A equals B, A squared equals B squared, show that A squared, given that A squared equals B squared, show that A equals B. You're not supposed to square root both sides because that doesn't show that they're equivalent. You might lose something. What you have to do is factor. So when I give you something like this, you're supposed to set equal to 0, factor it, and then solve it by using the zero product property. So let's keep in mind. You cannot, if you want to keep equivalence, you cannot square root both sides, and you can't square both sides. So let's do an example. Find a smallest positive integer a for which x squared plus a minus 2 plus a equals 0 has real solutions. So there's the key, right? A lot of this is knowing definitions. Real solutions means the discriminant is greater than 0. So that's what we have to do. We have to do the discriminant greater than 0. So the discriminant equals b squared minus 4ac. Since we say it has the real solutions, that this guy should be equal to 0. So my a is going to be 1 here, because I don't see a coefficient. B is a minus 2. And then C is A. Alright, so we're going to plug this in. So I'm going to get A minus 2 squared minus 4 times 1 times A should be greater than 0. Then we're going to solve this. This is A minus 2 times A minus 2. Distribute or do the box method. You should get A squared minus 4A plus 4. And then this gets me minus 4A greater than 0. Looks like the 4a is nothing. What am I doing? I get a squared minus 8a plus 4 is greater than 0. I mean, let's solve this. So we do lots of ways. It doesn't factor. You can do a quadratic formula. We can complete the square. It's been a while since completing the square, so I'm going to complete the square. So I'm going to subtract 4 from both sides. A squared minus 8a is greater than negative 4. And then we're going to get the middle term. Divide that by 2. Square it, so I get negative 4 squared, which is 16. I'm going to add to both sides. Oops. This side here factors to get me a minus 4 squared. It's always a thing before you square it. And then that's going to be greater than this, which is 12. That's 12. Now next I'm going to square root it, and then you might have to go, wait, that doesn't keep equivalence. Well, it does if you consider both portions. So we have a is greater than square root of 12, and or a is minus 4 is less than negative square root of 12. So you have to keep in mind both. If you want to keep equivalence, you got to keep in mind both possibilities here. Square rooting, and then you add 4. So I get a is greater than 4 plus square root of 12 is less than 4 minus the square root of 12. And if we approximate these, I'm going to approximate that in the calculator, I get about 0.536. And this is approximately 7.46. So we have a is greater than about 7.46 and a is less than 4.56. Now remember the question was, what's the smallest positive integer? So if we look at here, like, oh, 0.5 is small. Less than that is 0 though. And remember we talked about earlier? Or remember less than 0 is not positive. It's neutral. So it must be this one. A is greater than 7.76, which means a must be equal to 8. So that's the smallest positive integer for which this thing has real solutions. And that's a proof by equivalence, where even though it's not an equal sign, it's an inequality, it's the same idea. Right? We worked on both sides, we did all things that are mathematically equivalent to each other. I even took a square root, but as long as you keep both sides like positive and negative, then you're still a true statement. And that's the lesson.